Hello everyone, welcome to today's webinar on Unlock SRAM Repair Technology, Advanced Toolset with Siemens Tessent MBIST and eMemory NeoFuse OTP. I'm Sean Wu, and your moderator today. Today, I'm thrilled to have our guest speaker, Dr. M.Y. Wu, with us to talk about this cutting-edge advancement. Dr. Wu is an expert in the non-volatile memory technology and also the hardware security. With more than 20 years of experience under him, he has more than 200 patents filed and many awards received so far. And one of the most decorative one is the Best Paper Award from ISICC in 2018. So without further ado, let me give the floor to Dr. Wu.
Thanks to Sean's introduction. It's truly an honor for me to join today's webinar. And today I would like to go through our collaborative project with Siemens Tessent Memory Building Self-Repair Toolset. And I'm looking forward to getting into the detail. Okay, so any questions is highly welcome. Okay, let's get started.
Hello everyone. This is MY. This collaborative project with Siemens focuses on using OTP to repair faulty SRAM cells. These solutions can help SRAM's yield and reliability in advanced FinFET technology, especially for AI and automotive applications. Here's the agenda for today. At the beginning, I will use new pages to briefly introduce our proposed for new memory building self-test subsystem. And then I will introduce the recent development of OTP technology. Next, I'll introduce the main focus of our presentation, a new memory building self-repair solution. Finally, I will compare the benefits of this new approach with existing methods. Before we dive into the specifics, I'd like to give you a quick overview using the next 3 slides. Our primary objective is to integrate eMemory's high-capacity OTP technology with Siemens Tessent tool to enable more sufficient SRAM repairs than conventional methodologies. This slide illustrates the conventional approach to memory repair. Typically, the Tessent tool is used in conjunction with eFuse. Due to process variations or environmental conditions, SRAM bit cell may have defective bits that need to be repaired with eFuse. As we advance into the era of multi-core CPUs or AI applications, the demand for diverse and high-capacity SRAM continues to increase. However, as we scale up the capacity of eFuse used for repairs, whether it is 32 kbits, 64 kbits, or even larger, the area taken grows significantly. This creates a dilemma. One is the loss of area cost, and the other is the sacrifice of SRAM yield. In today's talk, I will present a new approach that integrates eMemory's high-capacity OTP with Siemens Tessent tool for SRAM repairs to resolve the dilemma. This method offers several obvious advantages over traditional eFuse solutions. Specifically, it becomes more compact, flexible, and reliable. I will deep dive into the details of these benefits and how they address the limitations of conventional methods in the following sections. Second part is about eMemory OTP latest update. eMemory currently stands as the world's largest pure non-volatile memory IP provider. Since the establishment of our subsidiary PopSecurity in 2019, We have expanded our offering beyond OTP and MTP-based IP to include digital and secure cryptographic IP solutions. Our robust patent portfolio, extensive technology platform, and dedicated R&D team provide comprehensive technical support, ensuring our customers achieve successful product development and mass production. Continuing from the previous page, it's clear that whether on FinFET platforms ranging from 16 FinFET Plus, N7 to N3E, or on the narrow-sheet platforms of N2P, eMemory's OTP technology is always at the forefront of this advanced process, ready for first-cut work and mass production. We have successfully supported many customers through smooth design integration, tape-out, and mass production, which stand as the best proof of our reliability and technical expertise. On this page, we categorize OTP usage into 6 main applications: security, identity, function, trimming, repair, and asset storage. The right figure illustrates how OTP capacity varies according to its application. Low to medium capacity OTP is typically used for system data, trimming, and security-related functions. Medium to high capacity OTP is employed for flexible boot code replacement. Additionally, OTP can serve repair functions, such as pixel repair of CMOS image sensor or memory repair. A notable trend is the use of high-capacity OTP for repairing SRAM or other types of non-volatile memories. In the next section, I will provide a detailed introduction to the solution we have proposed. Let me briefly discuss the current trends in SRAM repair. As SRAM technology develops, the static noise margin decreases due to the scaling down of process technology, power supply of VDD, or the demands of low-power applications for edge devices. In the figure on the left, the x-axis represents SRAM capacity. Historically, before the era of AI, SRAM capacities ranged from a few megabytes to tens of megabytes, typically used for CPU caches or general hardware accelerators. With the rise of AI, large language models, and new types of neural processing units, the demand for higher capacity SRAM has surged. Under these situations, we can expect a significant increase in the capacity of requiring OTP for SRAM repair, that labeled on the y-axis. This trend is closely linked to advances in process technology, expected yield performance, and the design of SRAM B cells, and caused the trend to move up and move down that I use line A, B, C to illustrate. Therefore, we have developed a new memory built-in self-repair system. As illustrated in the diagram on the left, this architecture integrates eMemory's OTP with Siemens Tessent tool for a comprehensive DFT subsystem. Tessent includes designs such as built-in self-test, built-in redundancy analysis, and built-in self-repair to achieve memory repair function. Previously, Tessent tool just uses eFuse via fuse bus interface. We have redesigned the connection interface by adding a synchronous interface for eMemory's OTP, and a universal interface to integrate with Tessent. This design can trigger Tessent tool can use eMemory's OTP solution. So how to use this new DFT subsystem? Here, I would like to firstly define our system as a dual-step memory built-in self-repair system. The repair strategies and procedures are as follows. Phase 1 is to get a defect-free OTP. The high-capacity OTP is self-repair first to be defect-free and achieves 100% yield. Phase 2 is to have the defect-free SRAM by using the Tessent tool to repair the SRAM array. In the following pages, I will walk you through each step in detail. This page shows the implementation details, and we can see that it contains the SRAM, Tessent tool, and eMemory OTP sections. First of all, SRAM is equipped with random bits to replace any bits that may fail if necessary. Next, the Tessent memory built-in self-test controller is used to test the SRAM. Following the testing, the Tessent built-in redundancy analysis module analyzes the defects and calculates the necessary repair information. Subsequently, repair information is transferred in parallel from the built-in redundancy analysis logic to the RAM repair ports and built-in self-repair registers. Following that, the repair information is transferred serially from the built-in self-repair registers to the Tessent memory built-in self-repair controllers. And then, compress and write the repair information into the eMemory NeoFuse OTP through the adapter interface. So how to retrieve the repair information that's stored in the OTP? First, the Tessent tool reads the compressed repair data from the OTP during device boot up. And then, this repair data is decompressed and serially loaded into the built-in self-repair registers. This patch data tells the SRAM controller to replace the defective SRAM bits with redundant SRAM bits.
Thanks, everyone. That's a lot of insight you have just shared. I think before the AI era, the SRAM capacity was just typically a few megabytes, like you mentioned, primarily used for CPU caches for hardware accelerators. But as AI surges and with the new LLM models, the NPU demands, SRAM capacity now is getting larger and larger. So actually that's a new set of challenge for designer, as you have talked about. So the question really is, for designers, how could they deliver a secure, reliable, and cost-effective solution with the limited time they have? So I think this pre-integrated SRAM repair toolset you just mentioned offer a great solution. But I don't think people are fully understand the benefit. Like, for example, there are a few questions that I already have. Like, what kind of an advantage does using OTP with Tessent have over using eFuse? And then, what are the key benefits of this dual-step built-in self-repair functionality will provide? Or even, what kind of application will be most suited for this? Can you elaborate a little bit further?
Yeah, thanks, Sean's questions. Yeah, Actually, your question is quite sharp. I have to say that currently we already have many customers already integrate our solution into their SoC. So I would like to use the following pages to introduce the solution's benefit.
I will introduce each feature in detail one by one. The first benefit is that if we want to repair SRAM, we must ensure that the non-volatile memory used to store the repair data must itself be defect-free. In this newly proposed memory building cell repair subsystem, eMemory OTP has designed the first automatic memory building cell repair. We have discussed two memory building cell repair concepts before, and I would like to emphasize it again. Phase 1 is to get a defect-free OTP. The high-capacity OTP need to be self-repaired firstly for defect-free and achieve 100% yield. Phase 2 is to have a defect-free SRAM by utilizing the Tessent tool to repair the SRAM array. The second benefit is that the capacity of SRAM repair using OTP is larger than traditional eFuse, providing better resilience against SRAM bit failures beyond the unexpected capacity. If the reserved eFuse bits are not sufficient to clear all SRAM defects, yield may be compromised. The third benefit is that at the same wiring distance, because the minimum VPP, VDD, and VSS resistance requirements must be met, the equivalent area of the eFuse will be more than 50 times that of the OTP. As manufacturing process evolve, the shear resistance of metal wiring decreases, making the floor plan of the using eFuse is becoming more difficult. This means that in advanced FinFET process, using OTP as storage is much simpler than using eFuse due to the relationship between programming current and power consumption. In terms of the most important in-field programming capacities, OTP also has great advantages. The fourth advantage is that OTP has lower programming energy and large capacity, so it can be programmed multiple times. It's particularly suitable for AI server, DPU, data center, and automotive-grade, high-reliability applications. The usage scenario is that we can repair the SRAM during CP stage or at FT stage, for example, after chiplet assembly or TSV connection, and then incrementally repair it over the times when it is shipped to the server or the car. We believe that this usage can improve the reliability of SRAM. The fifth advantage is that this memory DFT subsystems has been perfectly developed with Siemens, including our technical documents and possible integration problems, which have been solved, and customer can use it directly and easily. In today's talk, we propose a new memory building cell repair systems for future AI applications. The new system is developed through the collaboration of two leading vendors in DFT and OTP. Then, we provide not just conceptual solutions, but fully implemented and ready-to-deploy integrations. Third, the system features an ultra-high capacity OTP that ensures superior yield protection. Most importantly, the low energy required for programming OTP makes it ideal for in-field or on-system repair. This is especially valuable in high reliability applications, such as automotive, where optimal protection is critical.
Anyway, I truly appreciate your time you take with us today. I think MBIST, our solution, is going to be a key factor in the advanced SoC design from now on. So once again, thank you.
Thanks, Sean, and thanks to everyone's joining. We hope today's webinar can bring you new idea or new thought about the memory building cell repair subsystem using OTP solutions.
So the Q&A session are now open underneath. Please submit your question and we'll get back to you. With so many customers already adapting this solution, you shouldn't miss it. And thanks again, MY. We'll look forward to having you again.
Yeah, thank you. And any question is welcome.
The first question we have received talks about the SRAM repair solution. So MY, the audience is asking, is the SRAM repair solution you just mentioned easy to integrate? Any change will be needed for the current design, or anything should designers be aware of? I think people heard about what you talk about the benefit. Now they want to know what the cost might be behind it.
Hello, everyone. This is MY again. Yeah, I think this is a great question. We have taken this into consideration throughout the design of the solution. So that's why we co-work with the Tencent R&D team to pre-integrate all the components and necessary adapter. So the DFT designers does not need to do anything when using OTP for SRAM repair. Yeah.
So, MY, just to follow up with that question a little bit. So that means actually the OTP can be just dropped in and fully replace the eFuse and actually make the whole design more complete, better, since it offers larger capacity and a more comprehensive repair. Is that right?
Oh, yes, definitely. Yeah.
Thank you, MY. MY, the next question is following up with the incremental repair you mentioned briefly in the slide. So you mentioned about this topic with automotive or data center scenario. So what kind of integration challenges might arise, or how are they mitigated? Could this incremental repair help?
Oh, yeah, this question is quite sharp. If incremental repair for on systems or in-field maintenance is required, two things we have to consider and need to be met. The first, sufficient OTP capacity, which means that OTP needs to reserve space for in-field repair or on-system repair. It may need multiple times of capacity. A second, lower power operation of non-volatile memory. Yeah, for example, like program power is sufficient and important to support in-field repair. In-field programmability is a major advantage of NeoFuse OTP. And we designed these solutions can fulfill the requirements of high reliability automotive applications, data center usage, or AI application with large SRAM.
Thanks, MY. I think this should be really helpful for the audience. So for the audience, if you have any further questions, please, like our host has mentioned, leave them in the Q&A box in there, as we are going through the existing question and we will get to your question subsequently. And anyway, we have another question just came in. This is an interesting question regarding chiplet. I think chiplet is a very hot topic lately. And the question is basically, can this be applying chiplet technology? And or in other words, how would it help if I have a chiplet design?
Oh, this question is a bit difficult to answer, mainly because the current application direction is very diverse. More and more small chiplets are stacked and integrated in 2.5D or 3D according to the MCP, or for example, like TSMC CoWoS technique. It results in the CP or FT of the wafer not being easy to do a very complete test and repair before assembly or packaging. So we think that in the future, the OTP will be more and more important in the role of repair in the stage of post-assembly. We believe that OTP will play a more and more important role in the post-assembly stage in the future. Currently, some customers are already designing similar ideas. For example, like on-chip SRAM repair after assembly, or across-chip DRAM repair using Tessent tool, that with IEEE 1500 standard compliant. This is a brilliant questions and will be a future trend. So let's wait and see. Yeah, very good question. Thanks.
So NY, so when you mentioned about in the previous answer about doing the repair in the stage of post-assembly, that basically means like the in-field programmability you mentioned in the previous question's answer, right?
Most likely, because for current MCP or 2.5D or 3D advanced packaging, also is based on wafer labels. So it's not easy to do a very comprehensive sorting. So maybe current some new process flow or assembly flow that will be with rough sorting, and then after packaging do the assembly again. So not the 100% for the infill. It's most likely just after assembly. So using these solutions, that can be easily to do the repair or incremental repair during CPFT, after CPFT in assembly or infill or on systems. Yeah, that's what I want to mention. Yeah.
Thank you, MY.